So we have 6 different electrophiles that we have learned how to add to benzene, and one of them is a nitro group. If we add nitric acid and sulfuric acid, then we get this reaction called nitration that adds a nitro group. And that's useful putting one group on a benzene ring, but most of the compounds that we're interested in, most of the pharmaceutically interested molecules have at least 2 different groups on the benzene ring. So what if we already have a group on the benzene ring and we do nitration? Where does the nitro group add? And you have 3 different possibilities that it could add right next to the group that's already on there, forming the ortho product, or it could form meta, or it could add in the para position. So can we predict which of these products would form, or will more meta form than the others, will more ortho form, and why? So the answer to that question depends on the group that's actually already there. Not so much on the electrophile to add. So if we were doing, instead of nitration, if we were doing alkylation, then we would have the same 3 choices, ortho, meta, and para. And if there is a preference for the electrophile, whatever it is, to add in the meta position with one electrophile adding, it will also prefer to add meta with another electrophile. So it doesn't really matter what the electrophile is. What matters is what's on here originally. And let's think about why that is. So this group right here, this hydroxy group, has 2 lone pairs on it, and the first atom on that group has the lone pairs on it. And what you may remember from first semester is that if you have a group that has an electronegative atom with lone pairs on the first atom, I guess it doesn't have to be electronegative, but this one happens to be. If you have a group that has lone pairs on the first atom, then that group is an electron donating group, and we can draw resonance where we are taking one of these lone pairs and dumping it in there and making a pi bond, which would then make 5 bonds to carbon, and we would have to kick out the pi bond that's there and dump it somewhere else. So this is an electron donating group, and that lone pair, one of these lone pairs that is on the oxygen here, will be delocalized over the ring. And remember, the ring in this reaction is acting as what? It's acting as a nucleophile, right? We're always adding electrophiles, so it's acting as a nucleophile. And so if we are pumping electron density into the ring, then it's giving it more of a negative charge and making it a better nucleophile. And so let's see which carbons on this ring, the ortho ones or the meta ones or the para one, becomes a better nucleophile. So I'm going to redraw this down here so I can draw the resonance structures then. So OH, so I'm going to draw the same arrows I drew before, and if we follow those arrows, and you can go ahead and pause the video and draw the next resonance structure there, make sure that you know how to follow curved arrows. Put the bonds in the appropriate places and put the charges in the appropriate places, and then turn it back on. Okay, so we now have a lone pair and a negative charge up here. This bond and this bond are the same, and now we have a double bond here in between the oxygen and the carbon of the ring, and we have a positive charge there. And one way to check to make sure your charges makes sense is that the total charge before you draw resonance structures has to be the same as the total charge after you draw resonance structures, right? So this is zero charge and this is plus and minus, and they cancel each other out, so this has a net zero charge as well. And so what this shows is this carbon here that's ortho in one of the resonance structures has a negative charge on it, and so this is going to make it a better nucleophile in that position. So once we have that negative charge on the ring, what can we do with it? Well, we can dump that lone pair in here and make a new pi bond. And remember, there's a hydrogen on every single one of these carbons. So there's a hydrogen there and a hydrogen there and a hydrogen here. And if we did that, there'd be 5 bonds to carbon there, so we'd have to kick out the electrons and dump them onto the next atom, on the carbon there. So again, you can pause the video and draw that resonance structure. Okay, so what you should have here we now have a pi bond in this position, so this is a double bond here, and we have a lone pair, negative charge there, and then this pi bond hasn't changed, and we have lone pair and a positive charge there. And we can continue that around the ring. We can dump this in and pop the electrons on there and draw the third and final added resonance structure here. Okay, so we now have this pi bond is still here. We have flipped this in, so there's a new pi bond here, and then we have the lone pair and the negative charge in that position. So what is the effect of this hydroxy group on this benzene ring as a nucleophile? What you see is that that lone pair that's delocalized over the ring ends up in this ortho position, this para position, or this ortho position there. These are the only resonance structures that you can draw. And so the lone pair never ends up in the meta position. It ends up just in the 2 ortho positions and the para position. So when you look at this starting material, this reactant that's going to act as a nucleophile, then the picture you should have of it is this. There is a partial negative charge on the 2 ortho carbons, and there's a partial negative charge in the para position. So this is a better nucleophile in the ortho and para positions, which means that it's going to react faster. The electrophile is going to be attracted more quickly and react faster in the ortho positions and the para position. It's interesting that you have 2 ortho positions, and so if there wasn't any crowding effect here, then you might expect that you'd have more of the product that would be forming in the ortho position than the para position. So we add some electrophile, nitro, to it, and what we see is that the major products are going to be those where the nitro groups adds in the ortho and the para position. And the meta position, you don't see much of that at all. It's a minor product. So what we say then is that this electron donating group right here, this is an ortho para director. It is directing the electrophile that comes in to the ortho positions and the para positions. And so it's not distinguishing, and so you will get a bunch of ortho and a bunch of para and not very much meta. So, but there is definitely some regio preference here for the ortho and para positions. So when you see a group that is an electron donating group, it doesn't have to be a hydroxy group, it can be an amino group, it can be any group that has a lone pair on the atom right next to the ring, then you will see by resonance that it is directing the incoming electrophile to the most nucleophilic positions, which will be in the ortho positions and the para position there. Okay, in the next video we will look at what happens if we have, instead of an electron donating group on the ring, an electron withdrawing group on the ring.